For E95 compiler design and implementation, I have created a compiler that compiles a subset of the C programming language. The compiler begins with lexing and parsing. In this phase, C code is converted into tokens. The tokens are used by the parser to create an abstract syntax tree. Then the compiler uses the abstract syntax tree to create symbol tables and do a semantic analysis to make sure that the program is correct. Then intermediate representation code is generated. The IR code creates different steps that will eventually be converted into assembly instructions. Then the IR code is converted into assembly instructions. In this case, we're converting it into MIPS assembly language that will be executed on a SPIM simulator. Finally, the compiler performs optimization, where assembly code is consolidated, combined, and changed to run in a more optimal fashion. I created some extra features as well, including a test capture feature to quickly capture working code into unit tests, as well as a test loading function that loads existing tests back into my working directory. For my demonstration program, I made a MIPS program that multiplies a matrix by a scalar. Let's take a look at it. This program starts with a simple matrix and will multiply the matrix by a series of scalars that are stored in an array. Let's go ahead and take a look at the code. This is our simple matrix demonstration program. So this code here will be compiled by our new compiler. Essentially, we have a matrix, a simple 2x2 matrix, that's going to be multiplied by every element in this scalar. We also have a lot of UI interface elements here to tell the user what's going on. Each time the matrix is multiplied, this function right here is called. And here's the function. And so most of our multiplication is going to occur inside this function right here. So let's go ahead and compile it to MIPS. So we've generated a pretty substantial amount of code, and later on we'll take a look at how we can optimize that. Now let's run our code in SPIM on the class instance. We can see our initial matrix, and in this case we have 5 elements in our array, 0 through 4, and we can see that we're multiplying our initial matrix by each of the 5 scalars. Now that we have our code working, we need to optimize it. Before we optimize the code, let's start by increasing the number of scalars in our multiplication. Instead of 5, let's do 5,000. This will give us longer program run times and allow us to see the results of our optimization. We have 4 optimization levels available. The first optimization level removes unneeded goto statements and also unneeded address of or load address. Level 2 removes multiplication by 0 and multiplication by 1. Level 3 takes powers of 2 and changes them from a multiplication operation into a shift operation. And level 4 removes unnecessary load and store registers for the temp registers if they are not live across the function call. Now let's compare some optimized versions of our code. The first thing we've done is we've made a more complex version of our matrix program. It will run 5,000 elements and we'll time that using the time command. So we'll start with our optimization level set at 0 to give us a benchmark. It took a little bit more than 9 seconds to run without any optimization. Now let's try with optimization level 1. So we've been able to trim down to 7.8 seconds by eliminating unneeded go-tos and eliminating unneeded load addresses. Now let's try level 2. So now we're down to a little more than 7 seconds by eliminating multiplication by 1 and multiplication by 0. Now let's try level 3. So now we've been able to trim down to less than 7 seconds by also doing a shift left instead of multiplication by powers of 2. Now we're going to show optimization level 4. This level includes not saving and restoring temporary registers across function calls. Using this optimization level, we were able to get down to 6.2 seconds. We saw a substantial decrease in execution time at each of the optimization levels. Overall, we reduced execution time by 2.87 seconds, which was 31.6% of the original execution time. Now let's take a look at some of the elements that were changed or removed in the code. In the original and the level 1 optimization, we had 20 multi-use statements. Each of them had a move from low accompanying it. On level 2, we were able to reduce that by 10 to a total of 10 multiplication statements. In level 3, we got down to a single multiplication operation, and that one's absolutely necessary because it's the heart of the program. The other multiplication operations were able to be completely removed because they were all array management operations. And in this case, each of them was a multiplication by either 0, 1, 2, or 4. Not saving temporary registers across functions removed 208 memory access statements, and those were called frequently as we use a lot of function calls in our program. So we were able to do some great optimization, and I'm excited about the results. Thank you so much for watching.